Okay, hello everybody, welcome to this Giant Swarm Lightning Talk. My name is Christian and today I will talk to you about IPv6. So first of all, what's IP? IP stands for Internet Protocol. It is a foundational protocol in the TCP/IP stack. It is a protocol that allows routing to happen, or in other words, it allows network data to flow from one computer to the other. That's a very common protocol, and probably everybody of you is currently using the IP protocol to see this recording. The most widely used version of this protocol is number 4. It's called usually IPv4. It's been defined in an RFC 791 in the late 70s, so it's quite an old protocol now. And it's still in use basically everywhere there is a network of computers as of today. This is an IPv4 address, that 8.8.4.4. An address, it's a unique identifier for a network, for an interface for a device within a network. In IP version 4, the address is a 32-bit number. And that most often you will see written down as 4 integers separated by a dot, like 8.8.4.4. 32 bits means that we have about 4.3 billion unique IP addresses for everybody in the world. And back in the 70s, that was considered to be a reasonable number, but history told us that this is far from true. We started having problems with the number of IP addresses being too low many years ago now. And nowadays, especially with the rise of IoT devices, we really have the need to have many more IP addresses out there because we have more and more network devices connected worldwide. Throughout the years, to increase the lifespan of IPv4, techniques like the network address translation and NAT are in place to be able to reuse a subset of the IP addresses, the so-called private addresses, in different locations in the world, while keeping the public addresses unique worldwide, of course. Another problem, limitation of the IPv4 protocol is the presence of the broadcast traffic, so the ability for a network device to send network packets addressed to everyone else in the network, and that's potentially causing network congestion. So how did we come up to, what did we decide to do to solve this problem? What you see in the screen is an IPv6 address. Back in 1995, the IEEE began working on the successor of IPv4, and that's IPv6. The IPv6 address is a 128-bit number, and it's normally written in the form that you see on the screen. It's 8 groups of 4 digits hexadecimal numbers. They are called hexstats, divided by colons. It's obvious that this format of address is much harder to deal with for humans. So it's harder to remember, it's harder to communicate via voice, etc. But that's the price to pay to have 340 trillion unique IP addresses. So the number now is extremely high. So how do we help humans to deal with IPv6 addresses? There are 2 main rules for simplification. So starting from the same address in the previous example, the first rule is the remove leading zeros rule. So for each of the hexstat, you can remove all the zeros at the beginning of the hexstat, all but last one. So for example, in this example, we would end up in this simplified situation. The second rule is the contiguous number of zeros rule, and it allows us to take the zeros that are contiguous in the address, to remove them from the address and just leave 2 columns close to each other, like that. this can be done only once for a single address, of course, because otherwise it leads to ambiguity. This is not much better for human beings, but as I said, this is the price to pay to have so many addresses available. Okay, as in IPv4 we have different kind of addresses, such as public addresses, private addresses, broadcast, network, and so on. Also in IPv6 we have different kind of IPv6 addresses. The first kind is called the link local address. That's a non-routable address, and thus they mean they can only be used for the local network segment. Okay, they can't traverse routers. Then we have Unicast addresses. Unicast addresses are divided into 3 types, and they are routable, so they can traverse routers, and they can be global. Global unicast addresses are basically what we called public addresses in IPv4, so they are unique worldwide. Unique local, that are only routable in the private network, and Anycast, which is a special kind of unicast address that can be assigned to multiple devices at the same time. And they are basically used for kind of simulating part of the broadcast feature we had in IPv4. Finally, we have the multicast addresses that, again, are similar to broadcast in IPv4, but they are used in different scenarios. Okay, so the question is, how can we distinguish between the different types of IPv6 addresses? You can do it with the prefix, so by looking at the beginning of the address itself. For example, globally routable unicast addresses start with a 200 to be more precise. They are not all the unique addresses out there, but for now the IANA made available only those ones for everybody to use. Addresses that begin with the FC or FD are unique local addresses. Addresses that begin with FF are multicast addresses. For example, FF02 is the so-called all nodes multicast. That means that the packet gets delivered to every device in the network, like the old broadcast in IPv4. Finally, address that starts with FE80 are the link local addresses. The 64 at the end of the address indicates how many bits of the address itself represent the network part, and how many, by difference, represent the host-specific part. In other words, devices that share the same prefix, in this example the first 64 bits, are considered to be in the same network. Please note that there are no subnet masks in IPv6. This number is all we need. Yeah, and that's the prefix. Okay, let's now take a closer look at global unicast addresses. As we said, those are the public IP addresses, okay, and they are managed by IANA. So there is a central organization that manages them and assigns them. The first 48 bits of the address contains what's called the site prefix. The site prefix is defined in a hierarchical way, and basically IANA defines the that first 48 bits and assigns subsets of these first 48 bits by location, then by ISP. So the example here, the sample set prefix here might be assigned to a specific ISP in the US, for example. Then the ISP has the ability to set the last part of the site prefix, the last hextet, to their customer. Okay, so the whole site prefix is assigned to a specific company. Finally, the last hextet is available within the company for subnetting. Okay, and that leaves us with the interface ID. The interface ID is a identifier of a single network interface. So for each subnet, we have 2 to the power of 64 possible devices connected to the network, which is a huge amount. Okay, so there are a lot of features in IPv6, and I'm not able to talk about all of them, but I wanted to mention one, which is the SLAC, or Stateless Address Autoconfiguration. Basically, in IPv6, it is not required to have a centralized DHCP server for address configuration. Everything can happen in a stateless way, completely automatically. And that doesn't mean we have static IP assignment, but there is a procedure that I will describe right now. So when a new host wants to join the network, of course, it needs an IP address to be set. So first, it sends out in the network a special packet called RS. It's an ICMPv6 kind of message, and it's sent to all routers in the network automatically by using a multicast destination address, and it triggers. It requests basically all routers in the network to respond with a RA, router advertisement packet. The router advertisement contains the information that the device doesn't know by default, and more specifically, this is the site prefix. So once the computer receives from the router the site prefix, it is able to generate a complete IPv6 address that works in the local network. Because this generation is potentially based on randomness, there might be collisions. To avoid such collisions, the device, before using the new address, sends another message called the neighbor solicitation, using that address as destination. And the goal is to check that nobody is going to answer. If it gets no answers back, then it decides the address is free for use, and it starts using it. So it's it's all automated. There is no centralized entity that provides addresses. For the records, DHCP version 6 exists, and it still can be used. Because, for example, the SLAC protocol doesn't have any way to specify DNS servers within a network. So in some scenarios, it might still be useful to have a DHCP server. Okay, so last but not least, how much is IPv6 used nowadays? We said that the protocol is quite old. It comes from 1995, the first RFC. But there isn't been a real increase in usage of IPv6 before 2010. So about 10 years ago. This is a chart that you can find in the Google homepage somewhere, and basically shows how much traffic is going in the Google data centers using IPv6, and we are currently around just above 30%. And we are increasing about 5% every year right now, so we are not quite there yet, even though the situation is much better of a few years ago. Okay, thanks for listening.